Welcome back, everyone. Thanks for being here. So we've been sort of motoring through the course here, now done the second exam, almost done with Rankine cycles. So I thought it was a good time to kind of go back to the syllabus a little bit and update you on what's left. So we'll keep all of the assigned homework the same, but we freed up a little bit of room at the end of the course for review by... So I know you remember throughout the semester I asked you a couple of times here to watch a video by yourself at home. So that's given us a little bit of extra time. So today we're going to talk about another way that we can improve Rankine cycles. Then we have some internal combustion engine work. Then we'll deal with Brayton cycles, which are natural gas power plants. Then we'll talk about turbojet engines, which kind of have a Brayton cycle at the core, but of course we use turbojet engines to fly jets, right, airplanes. And then we'll talk about vapor compression, heat pumps, and refrigerators. And then we'll do a heat pump example. Now, I think the good thing about this is we'll have 3 classes at the end of the semester to do review. Now, I would like for those 3 classes to be as productive as we can make them. So I think as we get closer, what I will ask people to do is to bring in problems that they would like me to solve. And I'll kind of solve them in real time, having not seen them before, so that you get a sense of at least how I would approach doing an exam problem. So our final exam, right? So basically from here to the end, we're going through a bunch of different thermodynamic cycles. Now for all of these cycles, we're going to ask the questions like, how do we characterize the cycle? Right? Is it a heat engine, or are we trying to direct heat transfer? So are we trying to find a thermal efficiency or a coefficient of performance? Then we'll ask, do we assume that the processes are open or closed? Because that will tell us which versions of the first law, the second law we need to use. Do we need to use conservation of mass? And then the third question we'll ask is, what's the working fluid? Because after answering the second question, we'll basically have a bunch of symbolic solutions for our equations, but to get numerical answers, we'll need to fix the states. In fixing states, it matters if you're working with water going across a vapor dome, or if you're working with an ideal gas. And basically, the thermodynamic cycles that we look at kind of have different permutations of answers to those 3 questions. So we'll do a lot of cycle analysis problems. So what I imagine, at least what's happened in the past, is that when I've had these course review sessions, basically we'll get volunteers from the class to bring in problems of, maybe we'll vote on which cycles we want to go over, and then people will bring in those problems and I can solve them in real time to show you at least the thought process that I would have if I was going through an exam. So really, we want to really make good use of those course review sessions at the end of the semester. So I know that, for the review for the second exam, we ended up me just sort of giving my spiel for reviewing the second exam. But I think if you guys can be prepared with questions, we can make really good use of those review sessions. So today's lecture, the focus is on improving Rankine efficiency. So that's kind of what we've been focused on really since the second exam. We've been talking about different ways that we can improve the thermal efficiency of Rankine cycles. So last class, we focused on an example of reheat in Rankine, right? So remember, we split the turbine into a high pressure and a low pressure turbine, and we heated up or added more enthalpy to the fluid as it moved between those 2 turbines. And today we're going to talk about a process called regeneration. So remember, we're talking about heat engines, right? So Rankine cycles are heat engines. We know that when we're trying to characterize a heat engine, we take the energy benefit divided by the energy cost. The energy benefit in a heat engine is the net power that it generates, and the energy cost is that we have to add heat. We also know that the net heat or the net power is also equal to the net heat. So we can get this equation, and that's helpful, particularly if we're trying to do a Carnot efficiency of one of these cycles. So last class, if you remember, or maybe it was 2 classes ago when I was introducing the idea of reheat, I kind of think about reheat as adding more net work or getting more net work, and that's kind of driving up our efficiency. Now, of course, to do that, we had to add more heat, and it just turns out that we're generating more power than we're adding heat, right? So we sort of get an improved thermal efficiency. Today, we're going to talk about this regeneration process, and I think the benefit, at least in my mind, of regeneration is that we'll reduce the amount of heat that we have to add to the fluid when we're boiling it. Now, this comes at the cost of reduced net work, but here we're going to be reducing the input heat requirement faster than we're reducing the net work, and that's going to drive up our thermal efficiency. Right? So these are both strategies that you would use in a real power plant, and you wouldn't limit yourself to just one or the other. You would do both of these strategies potentially multiple times. So this strategy we're going to talk about today is called regeneration. So how does regeneration work? Right? So remember we talked about, kind of looking at these cycles as if we were master builders in Lego, right? So what we're doing is we're increasing the complexity of the cycle. So in a regeneration cycle, we still have split turbines. So we took the one turbine that we would see in the normal 4-component or basic Rankine cycle, and we split it into 2 pieces. But now, instead of reheating the fluid between these 2 places, what happens is we bleed off some of the mass between these 2 turbines. Right? So I think the idea here is that most of the all of the mass flow rate went through this high pressure turbine, the first turbine, and we get most of the power or a lot of the power out of it as we're going through this high pressure turbine. So now what we do is we bleed off some small fraction of the mass, right? Maybe it's something like, 10% to 20%, something like that, right? And this is still hot fluid, right? Because the enthalpy hasn't dropped as much because it hasn't gone through the low pressure turbine yet. So what happens is we bleed off this hot fluid and we send it into this open feedwater heater. But we'll get back to that in a little bit, right? So here the thing is we've split the mass. Now you might be thinking, oh, this is going to make my life more difficult. And that's probably true, because the good thing or one of the nice things about Rankine cycles to this point has been that all of our components were at steady state and had one inlet and one outlet. And that meant that the same amount of mass flow rate went through every single one of our components. But here we're splitting the mass, right? So maybe 20% of the mass comes out here. And that means the mass flow rate through this second turbine is different than the mass flow rate through the first turbine. So conservation of mass in these regeneration cycles are going to be important, right? Because if we take, say, 20% of the mass out after the first turbine, that means that 80% of the mass goes through the second turbine. And if you follow the line, it also goes through the condenser and through this first pump. But then the band kind of gets back together here in the open feedwater heater. Now, this is called an open feedwater heater because here the streams, they cross, right? I think I've told this story before, but this is a little bit like, my grandfather used to shave in an old sink, right? And the sink had a hot tap and a cold tap. So you would take hot water from the hot tap, cold water from the cold tap, mix them together in the basin until you got warm water, and he would shave in that warm water, right? So this is the equivalent of the open feedwater heater because we're directly mixing this hot flow that we bled off between the turbines with this cold flow that's already come through the condenser here. So this is going to be something that looks close to saturated liquid when it comes in here. But we're preheating it by adding this hot fluid in, right? And then what's going to happen is all the mass comes back together and the whole mass flow rate is going to go through this second pump, the steam generator, and the first turbine. So no one ever does this, but I always think they should, right? So I think you should bring colored pencils to your exam, right? So I think the benefit of that is it's going to make it a lot easier to track what the mass flow rate looks like in one of these regeneration cycles. So this is one of the trickier cycles. I think there's 2, maybe 3 cycles that are sort of, among the hardest that we do. Maybe everyone's got its own little trick. But this sort of tracking the mass flow rate is different than what we do for any other cycle. So I think if you bring colored pencils, you only have to think about this once during the problem. And then you can see what the mass flow rate is visually as you go through each different component. Now, like I said, nobody's taken me up on this yet, but you have the opportunity to be the first here. Right? Now, the benefit, again, of doing this is that because we're preheating, so what happens is this cold water comes in and mixes with this hot fluid here. And what that means is that some warm fluid comes out the exit of the open feed water heater. Now, that's pretty cool because the purpose of the steam generator is to add heat. Right? So the idea here is now that we've done this, this fluid at 6 has more enthalpy than it would have at 5. Right? We've increased the enthalpy of the fluid, which means that for the same that we, if we want to get the same inlet enthalpy going into this high pressure turbine, we have to put in less heat at the steam generator. So in a way, this looks like you're getting this heat for free, but that's not exactly the case. It's more that we've already paid for the heat because we're bleeding it off here at state 2. Right? So this is kind of like, sometimes a credit card or something, you get some free sign-up bonus with the credit card, but it's not really free. It's just paid for by the people who have paid interest on their credit cards. So the bank is trying to entice people to open credit cards, knowing that a certain percentage of them will end up paying interest, right? So this is the idea that this is sort of prepaid already, right? It's it's the free lunch that comes with a conference, right? You get that free lunch, except that it's not free because it's really included in your conference registration. So here, this is what we're doing in regeneration. We're preheating the fluid here. And what this means is we're reducing the heat that we add by a greater amount than the reduction in power that we get out of the low pressure turbine. And when we put those two things together, what happens is we increase our thermal efficiency. Right? So thermal efficiency, it goes down because we're reducing the amount of heat that we add in the boiler. Right? A consequence of that is that here we're increasing the average temperature of heat addition. Now, the textbook tells us that when we increase the average temperature of heat addition, then we tend to increase thermal efficiency. Right? We're also, because there's less mass flow rate going out or going through the condenser here, remember that the net power is the heat in minus the heat out. So we're rejecting less heat, right? So from a Kelvin and Planck kind of perspective here, if we're rejecting less heat, then that means that we must be having a more efficient engine, right? And that tends to be what happens here. So this regeneration process is Lorax approved, right? Because what it's doing is it's increasing our thermal efficiency, right? And that means that, yeah, we can make a better financial argument for doing this, at least in terms of operating costs, but it also means for the same amount of power, we're putting in less heat, right? Which, particularly if you're talking about coal power plants, that means that you're reducing emissions, right? And that's, as somebody who lives here on Earth, I think that's a good thing, right? So here, typically in the textbook, we'll talk about 2 different regeneration types. And these types of regenerators are classified based on the type of feed water heater they use, based on the type of heat exchanger that they use to preheat the fluid that's going into the steam generator. So here you have an open feed water heater. This is the case when the mass here from state 2 directly mixes with the mass here at state 5 inside the open feed water heater, and you get some warm mixture coming out that's somehow in between the 2 enthalpies of the inlet and the outlet. Right? Now over here, if we have a closed feed water heater, this is kind of the opposite, where the hot stream doesn't mix with the cold stream. Right? So these streams, they don't cross, right? It's like a shell and tube heat exchanger. So in this case here, then we're still transferring heat, but we're not mixing the mass together. So conceptually, these things are the same, where we're improving efficiency by preheating the fluid before it goes into the steam generator. But if you look at the plumbing here, the options are different, right? So here in the open feed water heater, we're splitting the mass out of 2. We have 1 minus the mass we're splitting out coming through here, and then we all come together at the exit of the feed water heater, right? But in the closed feed water heater, it's a little different. So here we split the mass out again at 2 between the high pressure and low pressure turbine, but it all comes together here in the condenser, So, the plumbing looks a little bit different. You're going to get different equations, right? And again, in a real power plant, you're probably doing both of these things at the same time. I see that Matt has a question. What's your question, Matt?
Yeah, so I was kind of confused. So it's closed in the sense that the water's not mixing, but it's not closed in the sense like a closed system, how mass can't go throughout it.
Yeah, that's a really good point, Matt. So the closed feedwater heater, you're right, it's closed between the two streams. So it does not directly mix. So the hot flow transfers heat to the cold flow, but does not transfer mass. Whereas in the open feedwater heater, they're mixing directly. So you're taking this hot flow, because they're both water, you're mixing them together in this reservoir, the open feedwater heater, and it comes out warm.
Okay, that makes sense.
Cool. Thank you for the question. So in both cases, we have some diverted mass flow, right? So it's y. Y is a fraction less than 1, right? And typically, it's much less than 1, less than a half, maybe on the order of 10% to 20% or 0.1 to 0.2. Right? So here again, I'm going to get my colored pencils out, at least digitally, and show you the path that this diverted mass flow takes. The non-diverted mass flow is 1 minus y times m dot, and that's going to go on a different path, right? So this reduced mass flow rate, in this case, goes through our low pressure turbine, our condenser, and our first pump. But here, it only goes through the first, or the low pressure turbine, and then it comes into the condenser, but this condenser is, when we come out of the condenser, we'll see we get the whole mass flow rate. So then the path that gets the whole mass flow rate is different, right? So here it's just the second pump, the steam generator, and the high pressure turbine. Here it's the first pump. Here there's only one pump. It's the cold side of the closed feedwater heater, and then it's the steam generator and the high pressure turbine. So hopefully you can see here that we're going to end up with different equations, even though sort of the general process is kind of the same, right? So what I'm going to do is I'm going to go through and develop expressions for the net power in both of these cases, right? So you can see sort of how to treat these regenerators, right? So if we got a regenerator, right? So I guess I'll do the net power and the heat in, because those are the components that we're going to want for thermal efficiency. The good news is when we're doing regeneration, there's no special new tricks to fix the states. So if you know how to fix the states in a basic Rankine cycle, so you know how to find things in two-phase mixtures, you know how to find the change in enthalpy across an ideal pump and then a real pump with isentropic efficiencies, then you can fix all these states, right? And there's no special tricks here, although we will get to, it's often going to be important to do the first law on either the open feedwater heater and then in the, if it's a closed feedwater heater, in the condenser as well. But I'll go through that at the end, right? So here we want to look at how do we get the thermal efficiency. So again, I like to get out this colored line and see what kind of mass flow is going through each component. And then I want to pay special attention to a component here like the open feedwater heater, where I have a different mass flow rate at each port. Here there's 2 inlet ports and 1 outlet port, and the mass flow rates are all different. That's going to happen at whatever place we have where the mass comes back together. So for this open feedwater system, I can look first for places where all of the mass flow rate goes. Now notice here in this table, the column that I have here is the mass flow rate through whatever component I'm talking about, which is defined by the inlet and outlet states, divided by the total mass flow rate, right? So here, 100% of the mass goes through the steam generator, the high pressure turbine, and this pump 2, right? Now, the next thing that I look for is where are my components that are getting sort of the undiverted mass flow, so 1 minus y. So 1 minus y, or if y was 20%, this would be 80% of the mass flow rate, goes through the low pressure turbine, the condenser, and the pump. Right? Now, this open feedwater heater is kind of special because it's different at every port. Right? So the mass flow rate changes depending on which port we're looking at. So here at state 5, when we're coming in, this is 1 minus y. At state 2, when we're coming in, it's y, right? That's the red line over here. And then coming out over here, that's the total mass flow rate at state 6. So this is a little bit tricky because sometimes when I'm talking about state 2, sometimes I'm talking about state 2 as the inlet to this low pressure turbine. And in that case, here, actually at the outlet of the high pressure turbine, I'm talking about state 2 getting the whole mass flow rate. At the inlet to the low pressure turbine, I'm talking about state 2 getting the undiverted mass flow. And then at the inlet to the feed water heater, I'm talking about state 2 getting the diverted mass flow. So we got to think about what's the mass flow rate at a given port in a given component, right? And it doesn't necessarily just get tied to one state, because one state can have different mass flow rates depending on which component we're looking at. So I like to make a table like this, and I like to draw on this with different colors, right? Because then that's kind of the same thing as having this table. It means that I have to think less. It's like I think about this once at the beginning of the problem, and then I implement a good process so I don't have to keep coming back and sort of doing the thinking over and over again. Because, each time you have to resolve a part of the problem, then you're sort of opening yourself up to making a mistake. Right? So now we want the thermal efficiency, right? The numerator in the thermal efficiency is the net power. So if I'm trying to find the net power, I look at the components that have the power term that I'm interested in, right? So turbines are producing power and pumps are consuming power. So if I make all the assumptions that I usually get, right, that I usually make, both of these components would get, or these types of components would have W dot is equal to M dot times H in minus H out, right? And the turbine powers are going to be positive and the pump powers are going to be negative, right? But I add them together. And in this case, there's 2 turbines and there's 2 pumps. So my net power term is going to have 4 different terms in it, right? One for each one of these components. So here I have the power through the first turbine plus the power through the second turbine plus the power consumed by the first pump plus the power consumed by the second pump. So I'm going to make all the same assumptions that I usually make, right? So I'm going to get the mass flow rate through the first turbine times H in minus H out plus the mass flow rate through the second turbine times H in minus H out plus the mass flow rate through the first pump, H in minus H out, plus the mass flow rate through the second pump times H in minus H out, right? And I do this because I would get these equations from the first law, and I let my sign convention deal with the signs. So I add all these things up, and the things that are going to be negative, I'm trusting to the first law to give me the right answer. And this is where it's different for the regeneration cycle, right? So if this was a reheat cycle, which had 2 turbines and 1 pump, it was still the same mass flow rate through all these components. But that's not the case here for regeneration. So I have all of the mass flow rate going through the first turbine. And then the reason, remember in that table, I talked about the mass flow rate divided by the total mass flow rate? Because then I can set my term up like this. So it still has the total mass flow rate in this, but now this is saying 1 minus y times m dot, right? So if y was 20%, then this would be 80% of the total mass flow rate. That's true for the first pump, and then the second pump gets all of the mass flow rate. Now, the reason that I do that is because each one of these terms is now still a function of the total mass flow rate. It's just some of them are multiplied by some fraction that's less than 1, right? So I can take little w dot net if I divide both sides of this equation by m dot total, right? So I can't do this at this point in the equation because these mass flow rates are different, or at least potentially different. But I can do that after I make these substitutions, because now the m dot is the total m dot through the system. So then I can get this expression, which gives me the net power per total mass flow rate flowing through the system as a function of the enthalpies and of this diverted mass flow rate y, right? So that's pretty good, right? But that doesn't help me for my thermal efficiency. Well, it helps me, but it doesn't get me all the way there because I still have to look at where I'm adding heat, right? Because my denominator here is where I'm adding heat. And in this particular cycle, there's only, or at least in this drawing for this cycle, there's only one place I'm adding heat, right? So it's a little different than the reheat cycle because I still only have one steam generator, right? So the heat in, or the sum of all the places where we're adding heat, is just the first place where we're adding heat. And that's going to be m dot through the boiler times h out, which is h1, minus h in, which is h7. So I know that mass flow rate through the boiler, if I look at that chart that I had, this is the total mass flow rate. So this is going to be m dot times h1 minus h7. So if I want to find the heat added per total mass flow rate flowing through the system, again, I divide both sides by m dot, and I get little q dot in is equal to h1 minus h7. Right, so now I can get my thermal efficiency for this open feedwater heater with regeneration, and it looks like this. It's a function of enthalpies and of y, right? Notice, in this case, I took little w dot divided by little q dot, but it would have been the same if I took big W dot divided by big Q dot, because then all the terms in the numerator and all the terms in the denominator would be factored by m dot total. So I could just take it out of the numerator and the denominator, and I would get the same answer. Right? It's always good if you get the same answer when you do the problem two different ways. Right? So here, I could use this expression, and if I knew the diverted mass flow rate, y, and I could fix all the states, then I'd be able to find the thermal efficiency. Right? Which is oftentimes, when we're doing these Rankine cycle problems, thermal efficiency is usually one of the things that we have to find. Right? And sometimes on a test, it would be broken down into different parts, like find the net work and find the heat in and then find the thermal efficiency. Textbook problems are like that too. But here we get this expression for thermal efficiency. So if we could solve all the states, then we could find the thermal efficiency here. There's a little bit of a problem though, because we also have this diverted mass flow rate, right? And sometimes the problem will tell you why, but sometimes you have to find why by yourself. So my general kind of idea or heuristic for when I'm trying to find this diverted mass flow rate, anytime really I'm trying to find a mass flow rate, I look for, do I know the net power or the net heat in? Or is there some component which has more than one inlet and more than one outlet, right? So if I was told the net power, right, if I knew the numerator here and I could fix all the states, then I would have an expression where the only unknown is y. Right? But oftentimes, if I'm trying to find a mass flow rate, I'm going to look for some kind of heat exchanger. Right? We saw that on the second test where we could find the mass flow rate of the cooling water by doing a first law analysis on that condenser, right? When we knew something about both sides of the condenser. So if we look at this open feedwater heater, right, and we do our first law analysis on this component, then we would say that it's at steady state, that even though there's going to be heat transfer happening inside the feedwater heater as the hot fluid mixes with the cold fluid, we'll say that it's adiabatic. So the whole thing is insulated, so we're not losing any heat to the environment. We're going to say that it's passive. There's no fan blades that are inside our open feedwater heater. We're going to say that there's no change in kinetic or potential energy, but we can't say that there's only one inlet and one outlet because there's two inlets and one outlet in this case. So generically here, we would find that the sum of m dot in h in is equal to the sum of m dot out h out, right? Or m dot exit h exit, right? Now in this case, I have two inlet ports. So if I took m dot total time, right? So because it's m dot times h, right? So m dot total times y times h2, and m dot total times 1 minus y times h5, right? So that's these two inlet ports. And then the outlet is just m dot total. It gets the whole mass flow rate. So this is times 1. And then we multiply by the enthalpy at h6. So here, if I knew h2, h5, and h6, then I could find y. Or if I knew y and I could find h2 and h5, then I could find h6. So that's kind of how we deal with the open feedwater heater, right? It's important to be able to fix our states. It's important to know which mass flow rates go with which component or which port of which component. And then it's also going to be important to do the first law on components that have more than one inlet and more than one outlet. So now let's look at the closed feedwater heater, and we'll really do the same process, but we'll see that when we follow that same process, we'll get a different answer. Right? And that's kind of, I think, the way that I'm trying to teach you how to do this class is if we have a good process, it doesn't actually matter what the components are. We just follow the process and we got a good chance of getting to the right answer. So I can ask you for a problem that's an open feed water heater or a closed feed water heater, or a problem that has an open feed water heater and a closed feed water heater and some regeneration between multiple turbine stages. And, the first time you looked at that, you might see it on an exam and say like, oh man, this is pretty scary, right? But if you slow down and you follow the process and you say, okay, I'm trying to find the thermal efficiency. So what are the components that are producing and consuming power? And where am I adding heat, right? And how do I get my symbolic solutions? Okay, now what's the fluid? How do I find the enthalpies, right? So if you follow this process, I think you'll get to a good result, even if it's a type of process you've never seen before, right? So this closed feed water heater is a little different. The plumbing's a little different, right? So we're still splitting off mass between our high pressure and low pressure turbines, but now it goes to this closed feed water heater, which is a shell and tube heat exchanger, where the hot flow does not mix with the cold flow. There's also this thing called a trap, right? So this is a valve. Its only purpose is to reduce the pressure. So you can see on this TS diagram, as we go from H7 to H8, we're reducing the pressure. Now, the thing that we would assume about a trap or a valve like this is that it's isenthalpic, right? Now, that's kind of you got to get, it's one of these words that you need your engineering decoder ring for. But if you remember what it means, or even if you don't, I guess I'm going to tell you, is that it means that the enthalpy across the valve is assumed to be constant. So here H8 is going to be equal to H7, but the pressure dropped. So it's a component, but it's not very interesting. Basically, it's steady state, no heat transfer, no power, no one inlet, one outlet, no change in kinetic or potential energy, and you just get that H in is equal to H out. So it's not very exciting. Again, I'm going to bust out my pencil crayons here, right? Or maybe that's a Canadianism, right? So maybe I'm supposed to say colored pencils here, right? So again, I'm going to look at which components get which mass flow rate, right? But in this closed feed water heater, it's maybe even a little trickier because there's two different heat exchangers, right? And remember, the heat exchangers are the keys to these problems, but they're also the tricky ones because they're the ones that have different mass flow rates at different ports. So it's true for the closed feed water heater, where both ports on the hot side get Y times m dot, and both sides on the cold side, or both ports on the cold side, get 1 minus Y times m dot. It's also true for our condenser, where we have a different mass flow rate at each port. So here I've kind of identified where my heat exchangers are. Then I'm going to see which components get the total mass flow rate. So that's going to be my high pressure turbine, my pump. There's only one pump in this case, not two, and my boiler. The low pressure turbine is the only component where both the inlets and the outlets are going to get the undiverted mass flow rate, right? That's at 80% of the mass flow rate in our example where Y is equal to 0.2. And then I deal with the condenser here. So the condenser's got one inlet that's coming in at 1 minus Y. It's got some other inlet that's coming in at Y times m dot. And then it's got this outlet, right? This is where all the mass comes back together. So the outlet here gets all the mass flow rate. On the cold side of the closed feed water heater, this should say closed feed water heater instead of open feed water heater, right? So here on the cold side, this is the heat, the fluid that's being heated up. It goes from state 5 to state 6. It increases its enthalpy, but that's the whole mass flow rate here. And then on the hot side, that's my red line. So here, state 2 and state 7 will get Y times m dot. So again, it's tricky, but I think we can make it more manageable by using colored pencils and by making kind of a little chart like this that tells us which ports in which components get which mass flow rates. So you can skip this step if you want to, but I think, again, if we do it, if we slow down, right, like Dora says, if we stop and think, then I think we got a better chance of getting a better answer. Again, our net power, which we need to find thermal efficiency, is going to be the sum of all the turbine powers plus the sum of all the pump powers. Here we've got two turbines. They're both generating power, right? So they're going to give us positive power terms. We've got one pump in this case. It's consuming power, so it's going to give us a negative power term. So here we've got W.T1 plus W.T2 plus W.P1. Now, if we can make the assumptions that we usually make, these are all going to be m dot times h in minus h out, right? So we know the inlet and the outlet ports, right? But now we got to remember that the mass flow rates through these different components are not necessarily the same. So here we got to go back to our colored pencil drawing, and we see that the whole mass flow rate goes through the first turbine and the pump, but only the undiverted mass flow rate, 1 minus y times m dot, goes through the second turbine. But once we do that, now again we have this total mass flow rate that we can factor out of all of these things, and we can find little w dot as a function of enthalpies and y. So now if I'm trying to find thermal efficiency, I also need where I'm adding heat. Again, here we're only adding heat in one case, right, in one component. So here we add heat in the boiler. So this is m dot boiler times h out minus h in. Now, I guess when you're looking at this, right, you could make the mistake of saying that we're adding heat here at the closed feedwater heater, but then you'd be double counting that heat, right? Because this is heat we've already paid for. So this heat that we're adding as we're going through the feedwater heaters are things that already were heated up in the boiler. We're just bleeding them off, right? So this is right, this is that free lunch that we paid for with our registration. It's already included, right? So here, this is just going to be the total mass flow rate times H1 minus H6, or if I'm looking for little q dot, this is going to be H1 minus H6. Now I can get, again, I can take little w dot divided by little q dot, and I can get an expression for the thermal efficiency for a regenerator. This again should say with a closed feedwater heater. And again, I'm left with this thing of, hopefully I can find all these enthalpies, but if I can't, how do I find y, right? So I need to find the enthalpies and I got to find y. So, how do I find y, right? Again, I'm looking for a case where hopefully I know the net power, but if I don't, then I want to look at doing the first law on a feedwater heater or maybe on a condenser too, because the condenser in this case will have some mass fraction that's related to y. Right? So here, if I do my first law analysis on my closed feedwater heater, then now I have two inlets. So I have this inlet, which gets m dot times y at state 2, and this inlet, which gets the whole mass flow rate times h5, right? So this is my inlet terms. My outlet terms over here, again, I have an outlet here at state 7 that's getting the diverted mass flow rate, and an outlet here at state 6, which is getting all the mass flow rate. So here you could see the mass flow rates would cancel out, and I could use this. If I knew y, I could maybe find h6 with this equation, or if I didn't know y and I knew all the enthalpies, then I could use this equation to find y. So here we'll go through a bit of an example. So if you were doing a homework problem, you're probably not going to see a case like this where this state table is so complete, right? Now, if it's a homework problem, you're probably going to have an almost empty state table. As we saw in the last exam, if it's an exam problem, you'll probably get a partially completed state table that's probably more complete than this one, or less complete than this one, but more complete than what you'd see in the textbook, right? So here, we just want to highlight that, I was saying, you could look for the total power, or you could do a first law analysis on the closed feedwater heater. But usually, if it's one of these problems, you're going to have to do both at some point, right? So you're almost always in these problems going to have to do a first law analysis on the feedwater heater. So if you get to a problem like this on an exam, if this ends up being on the exam, remember how I said if you're stuck, do the first law? If you're stuck on a regeneration problem, do the first law on a heat exchanger, because it's almost guaranteed to be asked at some point whether it's to find y or to find H6. Now in this problem, we're given all this information on the state table, we're asked to find y, and we're asked to find H6. So I've said that two different ways you can find y is you can look for a case where you know the total power, or you can look for a case where you want to do the first law on the closed feedwater heater, right? But in this case, they give us the net power, or actually in this case, the net power per unit mass flowing through the whole system, right? So this is going to be net power divided by m dot through the boiler. And we can use that to find the diverted mass flow rate, right? So here, for this closed feedwater regenerative system, we already have an expression for net power. We know that there's 2 turbines and 1 pump. We derived this expression already. Basically, we have the total mass flow rate through the first turbine and the first pump, and the undiverted mass flow rate, that's m dot times the 1 minus y, through the second turbine. But if we divide the whole expression by m dot, then we get that little w dot is equal to this expression, which is a function of enthalpies 1, 2, 3, 4, and 5, plus we need to know something about y. But in this case, on the state table that we were given, we were already told H1, H2, H3, H4, and H5. Right? So we're kind of in a happy situation where we know the net power per unit mass flowing through the system, and we know all these enthalpies, so we can use this expression to find y. Right? So I can take account of the stuff that I know, the stuff that I don't know, and the only thing that I don't know in this expression is y. And I'm definitely a happy camper when I got one equation with one unknown, because that means I can start punching stuff into my calculator. And in this case, the diverted mass flow was 0.23 or 23%. So the next thing it asked me was, what's the enthalpy at state 6? So this is the one thing that I didn't know in my state table. So, this is the point, right? Maybe you remember, I don't exactly know how to do this, but Dr. Scherzer said, when in doubt, do the first law. And if it's a regenerative problem, do the first law on a feedwater heater, right? So in this case, we have the closed feedwater heater. We know that this is going to be the sum of m dot in, h in is equal to the sum of m dot out, h out, right? We derived this already too, but the 2 inlets are here. We have state 2 coming in at y times m dot, and we have state 5 coming in at the total mass flow rate, right? So then I have on my left-hand side, m dot times yh2 plus h5. And then I have an outlet here at state 7 that gets the diverted mass flow rate, and an outlet at state 6 that gets the total mass flow rate. I notice that all of these terms are multiplied by mass flow rate, so I can divide by mass flow rate on both sides of the equation. So that's going to drop out. Now I've got an expression where I know y, I know h2, I know h5, and I know h7. So the only thing here I don't know is H6. So I can isolate for H6 here. And then I put some numbers into my calculator, and I find that H6 is 623.9 kilojoules per kilogram. So I know this wasn't an extensive example. And in your homework, you'll definitely have to do these problems, and they will take you far longer than the 5 minutes that we took doing this. And that's mostly because fixing the states takes a long time. But generally, fixing the states in a problem like this with regeneration is not much different than fixing states with a sort of basic 4-component Rankine cycle. Right? You'll need to be able to look up stuff that's under the vapor dome, things that are superheated vapor. You'll need to know how to find the saturated liquid enthalpies. You'll need to be able to find the enthalpy across an ideal pump. You'll need to be able to use isentropic efficiencies. But the one other piece of information you may need to use, like in this problem here, is you might also have to do a first law analysis on a feedwater heater or maybe the condenser to find a piece of information like H6. So this is one of the trickier types of problems that we do, because the mass flow rate is different through different components. Again, my advice is to bust out some different colors to remind yourself which mass flow rate goes with which port in which component. But that's all that I have for you today, and it actually ends our coverage of Rankine cycles as well, outside of the homework. So next class, we'll start to talk about internal combustion engines and the Otto cycle and the diesel cycle. So thank you for your attention. If there's any questions, I will field them now. If not, I wish you a pleasant evening, and I will see you on Wednesday. All right. Thanks, everyone.